In this video, we want to look at some fundamental integrals. Number one, the integral of 1 over 1 plus x squared dx is equal to arctan x plus c. Number two, the integral of 1 over the square root of 1 minus x squared dx is arcsine x plus c. Now, I want to take a look at an example. Suppose I want to integrate negative 1 over the square root of 1 minus x squared dx. Now, you can view this in two different ways. Notice that the derivative of arc cosine x with respect to x is negative 1 divided by the square root of 1 minus x squared. So if I integrate negative 1 over the square root of 1 minus x squared dx, I get arc cosine x plus c. Or if I have the integral of negative 1 over the square root of 1 minus x squared dx, I can pull the negative out. That is legal. And then I'm integrating 1 over the square root of 1 minus x squared dx. But if you go back to number 2, the integral of 1 over the square root of 1 minus x squared dx is arcsine x plus c. So over here, negative the integral of 1 over the square root of 1 minus x squared dx is negative arcsine x plus c. And those would be equivalent answers. Okay? Number 3, the integral of hyperbolic sine of x dx is hyperbolic cosine of x plus c. Number 4, the integral of hyperbolic cosine of x dx is equal to hyperbolic sine of x plus c. Now, let's talk about number 5. Suppose I want the integral of f prime of x divided by f of x dx. So what I'm going to do is I'm going to let u equal f of x. du is f prime of x dx. And so this turns into the integral of 1 over u du. Okay? Now, this is natural log of the absolute value of u plus c. But remember that u equals f of x. And so this is natural log of the absolute value of f of x plus c. So the integral of f prime of x over f of x dx is natural log of the absolute value of f of x plus c. So notice how we have the function in the denominator, but the derivative ends up being in the numerator. Now, so we're going to look at number 6. So why did I do that? Suppose I want the integral of hyperbolic tangent x dx. So this is the integral of hyperbolic sine of x divided by hyperbolic cosine of x dx. So notice how f of x is in the denominator and the derivative is in the numerator. And so this is natural log of the function, which in this case is hyperbolic cosine of x plus c. So it makes it real slick to be able to integrate something like hyperbolic tangent x. Now, number 7, right? Suppose I have the integral of hyperbolic cotangent x dx. Well, this is the integral of hyperbolic cosine x divided by hyperbolic sine of x dx. And notice here, in this case, my function is hyperbolic sine of x. But if I take the derivative, I get hyperbolic cosine of x. And so it fits really nicely. So this is natural log of the absolute value of the hyperbolic sine of x plus c. Now, you might ask, notice in number 6, notice how I don't have any absolute value bars around hyperbolic cosine of x, but in number 7, I do. Well, hyperbolic cosine of x is e to the x plus e to the negative x divided by 2. And this is greater than 0 for all values of x. And so I don't ever have to worry about the hyperbolic cosine of x being negative. And then if you look at hyperbolic sine of x, this is e to the x minus e to the negative x divided by 2. And there are values of x for which hyperbolic sine of x is indeed negative. So I do have to worry a bit about that. Okay, let's take a look at another example. Suppose I ask you to integrate cosine of x divided by 1 minus sine of x. I want you to observe something. If I let f of x be 1 minus sine of x, right? The derivative of f is negative cosine of x, okay? Now, what's missing? Well, what's missing in the numerator is the negative sign. So I'm going to put that in. So I'm going to write this as negative cosine x divided by 1 minus sine of x dx. But I can't just do that. I can't just put a negative inside the integral like that without offsetting it by a negative on the outside. Because remember, a negative 1 times a negative 1 is a positive 1, and then I don't change the problem on you. And then I want to circle back here to number 5. Notice that the integral of f prime of x divided by f of x dx is equal to natural log of the absolute value of f of x plus c. Now, let's go back here. Well, that's going to equal negative natural log of the denominator, which is 1 minus sine of x plus c. So notice there, no u substitution. Okay? On number 8, suppose I had the integral of f prime of x times e to the f of x dx. So if I let u equal f of x, du is f prime of x dx. And so we end up integrating e to the u du, which is e to the u plus c, but u is f of x. And so we end up with e to the f of x plus c. So it's really slick. For example, suppose I had the integral of e to the x plus e to the x dx. Well, I can write that as the integral of e to the x times e to the x dx. Now, notice that f of x is equal to e to the x, and the derivative of e to the x is indeed e to the x. And so the integral of this will be e raised to the e to the x plus c. Remember, my function is this e to the x piece. And it fits nicely into number 8. Okay. Let's take a look at this example. Suppose we're integrating e to the arc sine x divided by the square root of 1 minus x squared dx. Now, if it helps, we can write this as the integral of 1 over the square root of 1 minus x squared times e to the arc sine x. And we're going to integrate with respect to x. Now, notice my function is f of x equals arc sine x. The derivative is 1 divided by the square root of 1 minus x squared. Notice how that's here. And so it fits nicely. So the integral will be e to the f of x, which is e to the arc sine x, right, plus c. So I wanted to give you insight into how I'm thinking about these. And that's exactly what happened here. Okay? Now, let's take a look at an example here. Suppose I ask you to evaluate the integral from 0 to 1 of 3x plus 1 raised to the square root of 2 dx. Now, I want to show you something else. So let's come over here. Suppose I have the integral of f prime of x times f of x raised to the nth power dx. So in my mind, I'm doing a u substitution. We could write it down for now, which is fine. The inside function, notice, is f of x, so I'm going to let that be u. Du is f prime of x dx. Okay? And so this is the integral of u to the n du, which is equal to 1 over n plus 1 u raised to the n plus 1 plus c. But this is only true as long as n doesn't equal negative 1. Okay? Now, let's circle back. Suppose I'm given something like this. Now, my function is 3x plus 1. If I take the derivative, I get 3. But notice how I'm missing a 3. So I want to put that 3 inside. And in the parentheses, I still have 3x plus 1 to the square root of 2 dx, right? But I can't just put that 3 there. I have to offset it by a third. Because remember, 1/3 times 3 over 1 is equal to 1. Okay? And so I can do this essentially without a u substitution. And so here I'm going to get 1/3 times 1 over n plus 1, which in this case is square root of 2 plus 1, times 3x plus 1 to the square root of 2 plus 1, right? And we're going to evaluate this from 0 up to 1. Now, pop the 1 in. When I pop the 1 in, I get 1 over 3 times the square root of 2 plus 1 times 4 raised to the square root of 2 plus 1. Let's write that again. And then I'm going to put this in brackets. And then I'm going to subtract off 1. Now, the only thing I might do here is write this as 3 times the square root of 2 plus 1. And then in parentheses, I'm going to write 4 times 4 to the square root of 2 minus 1. And my thing is, I'm probably going to leave that alone. And it would depend on your instructor how far your instructor wants you to simplify or not. Okay? Now, let's come over here and let's do another example. Now, suppose I give you the following. Suppose I give you the integral from 1 to 4 of e to the square root of t divided by square root of t dt. So we'll do one more. Now, I want you to observe something. F of t is square root of t. The derivative of square root of t is 1 over 2 times the square root of t. Okay, so notice how my function is square root of t. When I took the derivative, I ended up with 1 over 2 square root of t. Now, if it helps you, I could write this as the integral from 1 to 4 of 1 over the square root of t times e to the square root of t dt. And so notice how I'm missing a 2. So I'm going to put it in. But I can't just do that. I have to multiply this integral by 2 as well, because it's like multiplying by 1. And it then becomes really slick. And so this is 2 times e to the f of t, which is square root of t, from 1 to 4. So notice I didn't do any u substitution. I mean, I'm showing you this to kind of give you insight into what I'm thinking. But I'm trying to get you to do a wider variety of problems without u substitution. And so this is equal to 2 times. Now, the square root of 4 is 2. So I'm going to write e squared. And then the square root of 1 is 1. And so I'm going to write minus e to the first. Factor out the e. And I could say 2e times e minus 1. And so that'll do it for this video. And we looked at a lot of fundamental integrals, and then we did different examples all in the process. So, okay, thank you.